Imagine scaling a transformer to a billion tokens. That would be something. Well, this paper does that, and we're going to see how they do that. The biggest problem with scaling a transformer up to a billion tokens is the quadratic complexity in a transformer, and they bypass this by making the attention linear and just dealing with the linear attention instead. And if you make the attention linear, then you can deal with it. You can deal with the quadratic. You don't have the quadratic complexity, so you can scale it to a billion tokens. And as long as you have the linear GPU capacity, then you can store all these. You can store all the tokens on, well, probably not on one GPU, but on a ton of GPUs. And you are able to do this. It is possible, unlike the quadratic complexity, which would be impossible because that would be a billion squared, and there's not enough compute power at all for that. So yeah, let's see how they do this. So to start, what is the quadratic complexity problem? Now I'm going to assume you already know how like a transformer works in general, but the quadratic complexity problem is, say I have sequence ABC. So ABC, I do not like that. That's too big. So say I have sequence ABC, then you know that, so you represent each of these, as a token, and each of these tokens has dimensionality d, and your sequence has dimension, it would be of length n. So you have a n by d matrix. And your n by d matrix, you will compute the queries, keys, and values from this matrix. So queries, keys, and values with a linear projection. And then your attention matrix is queries times key, or queries dot keys. So you get your n by n attention matrix, and then you multiply that by your values, and you get your output d by n matrix. And that's just normal attention. Of course, you have your softmax here and some regularization, but that is normal attention. Now, if we look at the sequence, you can see I have tokens A, B, and C. And if I draw out the attention matrix again, all tokens attend to every other token, and that means that there's a quadratic complexity. So our sequence length is 3, and our attention matrix is 9, so quadratic. If I scale this again, it would be A, B, C, D, so we would have 16 values that we had to compute, and that's the quadratic bottleneck. That makes our sequence O of n squared in time and in storage capacity, so the amount of time it takes to compute this matrix is O of n squared, and the amount of storage needed to store this matrix is also O of n squared. So you have both those problems, and both those problems are annoying to deal with. Now, what if we make this O of n? Then you can scale this, and it's a lot more workable. So that's what they do in this paper. Now to start, let's first take a look at an RNN and see what are the benefits of an RNN over a transformer. So if I have an RNN, then you know that an RNN takes in a hidden state, say H0, takes in our first token, say A, and then our output hidden state 1. And then we would take token B, put that through the RNN along with the new hidden state, and then that would output H2, which would be a new hidden state. It would be H2, and then you throw that through the RNN again, and then you get out H3, and so on. Now, what's good about an RNN? Well, an RNN does not scale if you train it smart. An RNN doesn't scale quadratically with the sequence length. And if you're just doing inference, then it only scales linearly because you don't have to store anything else. All you have to do is store H and the future tokens in the sequence. And the computation only relies on H and the token currently being inputted into the RNN. So the nice thing about an RNN is that it is linear with respect to the storage capacity and kind of the compute needed to use the RNN. In terms of time, it's also linear, so it's very nice. The bad part about RNN is you have to store everything in this H matrix, and the H matrix doesn't. It's a fixed size matrix, so you can only store so much. And if you increase the sequence length to infinity, then H is going to forget some things, and you're going to run into issues. Now that's why we use a transformer. And a transformer, if we have ABC, then the nice thing about transformer is it actually has the capacity, it has the complexity to be able to do complex relationships between A, B, and C, or between a sequence, which an RNN does not have. An RNN does not have the like expressiveness that a transformer has, but a transformer, on the other hand, it increases quadratically, and that's the problem that we want to deal with. So what's one way to approach this? So method one may be, okay, so we know our attention matrix is equal to the softmax of queries keys transpose. What if we were to approximate this? And some approximation methods have done, say, like using the kernel trick, where you have two functions. So you can approximate your softmax function or you can approximate your attention matrix using the kernel trick. And if you can find two functions, then you can successfully approximate this, but it'll make it a lot like it makes it not quadratic. It'll make it sub quadratic, and there have been methods to do this, but they haven't really proven to be super good. So that's one way of going about this. Now, what's another way of going about this? If we can't really approximate the attention matrix using like the kernel, then what's another way of doing this? Well, another way of doing this is you can kind of use a sparse attention matrix. I hope I drew that right. Yeah. So if we have A, B, C, D, E, F, then and then this would be A, B, C, D, E, F, then you know that this would be our quadratic matrix if everything attended to everything else. But if I were to, say, only attend to the nearest three tokens, such as this right here, so A, if I only attend to the nearest three tokens, then this is what the matrix would look like instead of being the full rank matrix. It would look like this, something like this. So now we only utilize part of the matrix, and this is more of a linear complexity. But now this is more of a convolutional neural network because it's a lot more local for what the tokens can attend to, and that's the problem with this method. And you can add more representation power to this matrix by saying, well, I know that maybe A is our classification token, so maybe everything needs to attend to, or maybe A needs to attend to everything, something like that. But these methods haven't really shown to be a lot better, and usually you'll end up with something that's log. It's not linear. Usually you'll end up with like a log complexity as opposed to the desired linear complexity whenever you're doing something like this. I think Big Bird I think that was log complexity. I may be mistaken, but I think that was log complexity, and that was one way they did something similar to this, and it didn't quite show to be super impressive. But yeah, that's another way we can kind of make attention sub quadratic. Now, a third method is, well, what if we do a window attention? So say we have A, B, C, D, E, F. So if I do attention on all this, then A would attend to everything. But if I do a windowed attention, maybe I would say split my sequence in half and only do attention, or maybe split my sequence into pairs of two or something like that. Then this would only attend to here. This would only attend to here. So, and this is our attention. So our attention would only be on the sub keys, or on a subset of the tokens. But then you end up with another thing, or then you end up with convolutions again. So you want more representation power than convolutions because convolutions are so local, and that's the good thing about attention. It's not local, it's global. But the problem is everyone that tries to make quadratic or subquadratic attention, it ends up being a more local strategy. But this paper shows that you can kind of do a local and a global strategy at the same time to get to get linear complexity, but it also has great representation power like a transformer. And that's what this paper does. So let's get into their method. Yeah, and they show here that like a recurrent neural network, that's linear, but yeah, it's linear with respect to the sequence. Regular attention is quadratic, and then sparse attention is n root n, so subquadratic, but still not that good. And it also doesn't have the representation power that you would want, but dilated attention is what they call it. And if you've heard of dilations in convolutional neural networks, then it's very similar to that. But yeah, they use something they call dilated attention, which is linear with respect to the sequence length. Now, how do they do this? So they have this, they show it off here for how they do it. So let me just show you this. Let me just show you this first part. So say we go with the local method. Say we start with, so this is our attention matrix, and this bottom part here would be our keys, and this would be our queries. So if you look at this, you can look at this and say like the queries are like if our sequence is 1, 2, 1, 2, 3, 4, 5, and so on, 1, 2, 3, 4, 5, then you can see that 1 only attends to itself because this is causal attention. Notice how like it's the upper triangle does not have any attention, is not being attended to, and that's because of the causality that you want to add to attention to make it a generative model, like a GPT model. But you can, if it wasn't causal, then you would fill this whole mask. But yeah, anyways, you can see how token 1 only attends to token 1 here, but token 2 has token 1 attend to it, while it also has itself attend to it. And then token 3, you would have 1, 2, and 3, and that's the causality. But anyways, notice how this big part right here is missing. And what they do here is they do a local method. So they have a local method of, or they have a local window of size 4. And in this local window, everything can attend to everything else. So you can see if we were to fill in the rest, so if this was like that, then everything in this window can attend to everything else. But outside the window, nothing can attend to that window. And then if you look at the next window, you can see everything can attend to everything else in that window. So if we look at our sequence A, B, C, D, E, F, or 1, 2, 3, 4, 5, 6, then it's kind of like breaking up the sequence into the windows I showed earlier right here. So if we break it up like this, then A, B, and C would go through attention independently of D, E, and F. So these would attend to each other independently, and that's what's happening here. So this is a local attention. Now, what if we kind of do a dilation? What if we what if we increase the window size, but we also we do a sort of dilation in between the attention scores. So 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. Again, this is causal, so the upper triangle is not attended to. But notice how token 1 attends to token 1, nothing attends to token 2. So we skip over token 2 because we have a dilation rate of 2. So we're skipping over we're basically skipping over one token. So now token 3 has token 1 attend to it, but notice token 2 is missing. And we skip token 4 because we have the dilation rate of 2, so we basically skip over 1. Now you can see token 1 and token 3 attend to token 5, and so on. But notice how this also has a local capacity. It's also kind of local because we only have we have a local size of they call segment length of 8. So what you have here is you have a dilation rate of 1 with a smaller segment length, a smaller window size, but you increase the dilation rate by 1, and you double the dilation rate, but you also double the segment length. And notice here, they do it again. So you have a local window, but if our size is 16, then, and our window size is 16, then it becomes global. And notice how the global attention is very spread out. Like you have token 1, 2, 3, 4, and 5. And notice how 2, 3, and 4 are not attended to at all. There is no attention going to 2, 3, and 4. 2, 3, and 4 are not attending to anything else. Within this window, it's only tokens 1, 5, 9, and so on. And it's very sparse. Now, all three of these alone would be very bad. It wouldn't be a good attention matrix at all. But what if you were to add these together? Now you can see we have this locality here between very nearby tokens. But see, we have the locality, but you also have global attention scores that are being computed. So the idea is if you have a sentence, then local information should attend to each other should attend to each other like local information should attend to each other. That's very important, the local area, but global information should be attended to each other over time. So it's not as important for it to be attended to immediately, but it still should be reached as you increase the number of layers. So as you increase the number of layers, this attention matrix kind of grows, the receptive field. If you've seen, say, if you've seen a dilation and convolution, you know that as you increase the number of layers, the receptive field grows. Here, let me show you over here. It's easier to see with a 1D sequence. So if I had, say, like if I had a normal convolution, this is a 1D sequence, and this is a 1D convolution. If I had a normal convolution, you know that the way you would compute your 1D convolution would these values would be multiplied by the filter. You add them up, and you get your single value here, and then you slide your filter across your sequence. But in a dilated convolution, you would do something like this, where you would take the value here, here, and here, and you skip over one of the values in your sequence, or one of the tokens. And now the receptive field is a little bit larger, because notice how the convolution can broaden what it can see. Instead of it just looking at these 3 values here, it's looking at 5 values and skips a couple. And if you've seen, and as you add the number of layers, as you increase the number of layers, it's able to look at more of the sequence. It's kind of hard to draw out here, because if I have another this would output 1 value, and if I have another convolution, it's hard to draw out. But as you increase the number of filters with a dilated convolution, it sees more quicker, so it increases the receptive field, and that's what also happens here. Now, the way they do that is down here. So the biggest problem with this is if you have this idea for a sparse convolution, or if you have this idea for a sparse attention matrix, you have to actually implement it well. If you do all the computations and then you just mask out some of them, then it doesn't really mean anything because you did the n-squared computation. So you have to have some way of only computing these values. And they do so in a distributed way. You can do it on multiple GPUs, but what you do is you split this into multiple heads, and we'll get into what the multiple heads do. But yeah, you split them into multiple heads. You compute the queries, the keys, and the values. And then what you do is you only, so yeah, they just say sparsify. You only select the query keys and values that you need for the computation, and then you do the computation. They have some math over here, but yeah, what you do is you only collect so you first segment the sequence, and then you only collect the query keys and value parts that you need. So instead of saying, well, I need my entire sequence and then I need to compute my entire sequence, you only take the parts that you need and do the computations on those. And you can do this with like some customized CUDA kernel probably, but it's not too important how they do that. So you don't do the entire n-squared computation and then mask it. You specifically do these computations here and these computations here independently from the rest. So you only do the little computations as opposed to the whole n-squared computations, and that's what makes it sub-quadratic. So it's very, very nice way of doing it. Now, what kind of makes this different from other methods is the way they construct this attention matrix, which allows the information to flow well. And they kind of have a bunch of proofs down here. And one of the more important ones, or I guess not proofs, but more formulas. And one of the important ones is this one here. So say we have this attention matrix. Now, the important thing is for information to flow. That's the important thing about attention. And since we don't have global attention, then you don't have everything attending to everything else. But hopefully it's close enough to that. Hopefully we have an almost full attention matrix. At least if we increase the number of layers, hopefully it'll be able, everything will be able to attend to everything else quickly. And due to the nature of these dilated convolutions, this does happen. So this formula states that the approximate token dependency, so that's what they say here, the approximate token dependency is O of log n. So that means that the maximum path length it takes, so I have over here, maximum path length it takes for one token to attend to any other token in the sequence is O of log n. Let's kind of, I kind of have an example here. So we can't attend to everything within one layer, but what if we have, say, 2 layers? In this case, we can attend to everything within 2 hops due to the relationship they show down here, this equation. If you do the computation, which I did right here, then you can attend to everything in 2 hops max. So let's just do 2 to 4. So say we go from token 2 and we want to get to token 4. 1, 2, 3, 4. So how many layers will it take to do that? Well, if we look at token 4 and then we look at token 2, then token 2 can directly attend to token 4. So that's 1 layer. But if we look at token, say we want to go to token 2 to token 5, then, so right here, 5. But notice how token 2 cannot directly attend to token 5. However, token 2 can attend to token 3, so token 3 right here. Token 2 can attend to token 3, and then token 3 can attend to token 5, so that's 2 hops. And you can attend to everything within this matrix within 2 hops, and the number of hops is the number of layers. So if you have a sequence size of n, or of 16, in this case it's 16, then you can attend to anything within 2 layers, which is pretty good. And it's a log relationship, so as you increase the sequence length, the number of hops or the number of layers needed to attend to anything within the sequence is O of is a log relationship, which is it's pretty good. It's not perfect. You can't attend to everything within one layer, but it's not bad. And they show that you get good performance even with this kind of issue. But the trade-off is you get linear attention by using this, and they show that here that you can. They show here that the attention is linear. So they start off with this right here, this equation right here. How many flops does it take to compute our attention matrix? And you can see there's kind of two important terms. The first term is n over w. So n is our sequence length. N is the sequence length. And w is our window size. So if we have, say we have like a 3x3 matrix, or not a 3x3 matrix, but say we have a 9x9, or say we have a sequence length of 9, then it would look something like this, like that. And then you would cut, and our window size is 3, so this is n is equal to 9, and w is equal to 3, and r is equal to 1. So r is the hop length, but the hop length is annoying to draw out. So we have this sequence that is n is equal to 9, w is equal to 3. Then in this case, our equation, or we would have 3 windows because that's 9 over 3, so that would be 3 windows. And for each window, we have to do w over r squared computations. So w over r squared is the number of attention computations we have to do per window. So that is equal to 3 over 1 squared, which is equal to 9. So the total number of computations we have to do is 9 times 3. So 9 times 3, that's the total number of computations we have to do. And then the d term right here is because you're doing inner products, so you're not doing scalar multiplication. So the d term is just there because we're doing inner products. You're multiplying the vectors together, not scalars. And the 2 term right here, I think, is just for an upper bound. I don't know exactly where that comes from, but the other terms here, you can kind of see where that comes from. Now, this is just for one of these matrices. It would be for this one right here. And you can just sum up the complexities for all of these matrices here, and you get this term right here. 2 and d are constant throughout the entire computation. wi and ri change. wi is the window size, and ri is the hop length in the window size. And then they show that you can you result in this equation where alpha is the ratio for geometric sequences, w and r, and you get this term for the number of flops needed to compute your attention matrix, and this is linear. It's linear with some terms out in front, but it is linear in terms of the sequence length, which is very nice. That's what we were looking for. And if the results are good, then this may be a really good approach to linear attention, which we all really want. Now, yeah, that's how they that's kind of the proof that they show to show that this is linear. They also show that information has a maximum distance within a sequence, so you can't attend. I guess you can attend, since this is for 1 billion tokens, you can't attend from like token 1 billion to token 1, but you probably wouldn't need that in 1 billion tokens. But yeah, they show that it also has a maximum distance here. But yeah, that is the method they do. Additionally, they note that you cannot do this on a single GPU because you can't put a billion tokens on a single GPU. So what they do is they split X, so our original sequence, into G sequences, where G is the number of GPUs. So you split this up evenly. You compute your query keys and values, but the problem is, like I show here, is if you have x1 and x2, then x1 and x1 attend to each other. That's fine. x2 and x2 attend to each other, but you need to have this shared value. So for GPU1, you kind of have the keys and the values from GPU2 go to GPU1, so you need to share those, the keys and the values. And you do the same from GPU1 to GPU2, and then you compute your final attention scores using those. But yeah, they show that you can parallelize this really well by just splitting the sequence basically down the middle if you have two GPUs. So that's very nice. That means that you can parallelize this really easily. And if you use flash attention, which is what they use, which makes it faster, attention faster on a GPU, then you can do these computations really fast, even if you have a billion tokens. So yeah, I mean that's the method. It really isn't too bad. All it's doing is making this using these dilated attentions and then adding them together. They also show that you can make the receptive field increase even better by splitting it into different heads. And instead of having the same head be the same matrix, so if you just had 4 of these matrices, you can actually move the you can actually move the attention scores down a little bit. So instead of it being the exact same, notice how it starts here instead. And this way you increase the receptive field even more. And they show that this is better than doing it normally because your receptive field increases faster instead of it being the same matrix. So the number of heads actually, so more heads may actually be utilized better. Usually, if you have, say, 8 heads, then only 2 of them will be used a lot, but in this case, maybe they will be used even more rather than kind of being there and kind of being useless. But yeah, that is the method. So let's see the results to see how well this actually does. Is this linear attention actually good? And it turns out it is actually pretty good on the one kind of task they do. I wish they had more tasks, but they only have one in this paper. They only have one score table in this paper, and this is the score table. If they're measuring against sparse attention or a sparse transformer, which we showed up here. Sorry, they showed up here. It's n by root n d. That's the computation complexity, and they wanted to show that their method, which is linear, is at least on par. But in this case, it does better than the other methods. So your base transformer, it can't scale past any reasonable amount of tokens. The sparse transformer can, but it's much worse than their transformer. You can see that the perplexities, which you want to be lower, are with 2K tokens, they're about the same, but once you get to 32,000 tokens, it's a big drop in perplexity, meaning that it is a lot better. It's a lot better at utilizing it's a lot better at utilizing the tokens than the sparse transformers. So the sparse transformer may be able to look at all 32,000 tokens, but the expressivity, it's not very expressive in how it can use those. While the LongNet, this transformer, can actually use all 32,000 tokens, or at least it can use 32,000 tokens better than the sparse transformer. Now, what about the billion tokens that I promised at the beginning? Well, this is kind of all they show for the billion tokens. They show that as you increase the sequence length, the vanilla transformer, it increases quadratically. And notice how this is it's not a log scale, it's a normal scale. and this does increase linearly, and this does increase quadratically. So that's all I got to show you for the billion tokens. They don't have any scores to show that it does perform, how it performs, but they show that it can go to a billion tokens, which is kind of cool. But also, I wish they showed a little bit more than just saying, yeah, we got a graph that shows we can go to a billion tokens, but that's what they show, and that's what we got. So we can take their word for it that they got to a billion tokens. I'm not sure if they published the weights for that, but that would be maybe a lot of weights. And they also show some other graphs, like in this graph, the perplexity of a normal transformer as you increase the number. As you increase the number of flops, the normal transformer here, it takes a lot more flops to have a lower test loss, while in this case it doesn't, just showing even more that it has linear complexity while the transformer does not. This is the graph. So on the left, you can see that as you increase the model size, of course, the test loss goes down, but on the right, you can see that as the context window increases, the test loss goes down, which just shows that scale properties do hold for even sparse attention, which is kind of cool. That you don't need full rank attention to have the scaling laws that you see in normal transformers. As you scale the number of parameters, you usually see that it does a lot better, but in this case, you don't need full attention to have these scaling laws. You can have sub-quadratic attention and you still have these scaling laws. So it's very nice that we have the scaling laws even if you don't have full attention. And yeah, that's pretty much the paper. They don't show too many results, and I wish they showed a lot more, but yeah, that's the paper. And it's a cool method, and I'm curious to see if it gets used more than normal attention. But yeah, there you go. Billion tokens.